Okay, good afternoon. So now we are ready to face the big problem. How do we solve an inverse kinematic problem? We have seen that there could be a different number of solutions. We have analyzed the fact that we should make sure that the data are within the workspace, but then how to solve the problem. And we will see today some analytic method and some numerical method for solving the same problem. In doing this, especially for analytical method, we will see that there are checks that we can do in order to discover if the data are solvable. So, for instance, if the data belong to the workspace. So we don't need to worry in advance about that. For numerical method, instead, this is an open issue. So the algorithm may stop after some iteration just because the solution is unfeasible. Okay? So take this in mind. So analytical solution means also looking for the expression of the joint variable in a closed analytic form. So we have formulas. You put in the data on the right-hand side. On the left-hand side, you have numbers. And you may have this formula combined so that you may generate more than one solution. Certainly, you cannot generate an infinite number of solutions. So the analysis that we have already made tells us that those cases should be handled with some if in your program code so that you avoid doing things that do not lead to even multi-valued function. So what can we say in general? Looking for a solution in closed form is preferable. Why? Because you code this once for all for your robot and you're done. Okay. Of course, if you can find it. And that star on the text means that there are sufficient conditions that guarantees you that you can find a solution to your problem in closed form. But if those are violated or do not apply, then nothing can be said in advance. Okay? How do you proceed in that case? Well, in easy cases, you use some geometric introspection. So you will see some example. It's pretty much clear. Or, as I've shown on the blackboard last time with a simple example of a trigonometric function equation that can be transformed into a polynomial equation, we made an example with a transcendental function equation converted into a polynomial equation of degree 2, so that we can say that there are at most two solutions. We are all interested in real solution in that case, so that we can, when we map back the solution into the original joint variable, we have real numbers. So solving polynomial equation. But this is not a really efficient way. It's just when things get very complicated and you don't know how to deal with. For instance, algebraic method of the interval type are recently been developed for solving a problem of kinematic, in that case direct kinematics, for parallel kinematic manipulator. You remember that distinction, where the direct kinematic is tougher than the inverse kinematic in that case. Or you may have some systematic ways for generating a reduced set of equations to be solved. Remember that if we start with a classical problem, so we are giving a pose for the end effector, so a rotation matrix and a position for the origin of the end effector. From there, we equate this with the direct kinematics. So in principle, we have 3 by 3 for the rotation plus 3 for the position. So 12 equation in a certain number of unknown, n, the number of joints. And these equations are nonlinear. So even if we restrict the case to n equals 6, where it makes sense to look for a solution in closed form, then we have probably too many equations, 12. There are ways in which we can extract from this 12 equation a reduced number which is good for making computation. I make two examples. First example, suppose that you have let's say, a 6 degrees of freedom robot, and you assign this matrix. Remember that this is R06, P06 expressed in 6, and then 0 transpose 1. Okay, these are the 12th number plus some default row, the last row, that are given. And suppose that your robot has 6 joints, so that you have this type of kinematic equation up to A5, 6 as a function of Q6, and these are the unknown. Okay, so you have to solve the upper part 12 equation. These are the data, and these are the function of Q1 to Q6, 12 equation in 6 unknown, nonlinear of type. Now you can look at the individual equation, trying to find if possibly some equation is simpler than the other. We have done already this when solving the inverse orientation problem for using minimal representation of orientation with triangle of, let's say, the Euler type. We have looked at the final rotation matrix and identified the elements which were simpler and that we can could elaborate. Okay, something similar can be done here. For instance, Paul's method and you have in your material the original paper of Richard Paul that solves the inverse kinematic for the Unimation Puma robot, and he did the following. It's a systematic way of generating equation. It's not really a solution to the problem, but it's a helpful hint. So he considers the following. Look at this equation. And now suppose that you pre-multiply this by the inverse of A01. Okay? So you will have A01 to the minus 1 as a function of Q times T06 equal A12 Q2 up to 5, 6 Q6. Now, what you have done is maybe you have generated a new equation, and at some point you may have a function which is only an equation which is only a function of Q1. It's not guaranteed, but this may be a way for generating things. Or post-multiply things by the inverse of the last equation. And you have this type of relation. Again, if you're lucky, you may find some equation that are simpler and possibly depend only on one variable. If you do so, you can solve for that variable, and now your problem is reduced of complexity, and so on and so on. You can continue to pre-multiply by the inverse of those transformation matrices. These are the Denavit-Artenberg homogeneous transformation matrix, or post-multiplying on the right-hand side. Okay, and this is one way for generating things. There's another way which is due to American researcher Mansur and Doty, that is able for a 6 degrees of freedom revolute joint arm to extract 4 equations from the data, and then from those solve for 4 variables, and then the first and last variable Q1 and Q6 are solved easily once you have isolated things. One of these equations it's pretty much simple. Look at this and compute the norm square of this, which means essentially you do the scalar product of this by itself. Okay? So these are numbers. Of course, the same should be true on the other side. Equal some function of q on the right-hand side. When you do this product as a function of q, this is a number. And my bet is that this is, in fact, a function only of q2, q3, q4, and q5, not of q1 and q6. Why is that? Because what is this, in fact? Is the distance, the square of the distance between the origin of frame 0 and the origins of frame 6. Now, this distance is independent of the fact that you're rotating the frame 0, so by around frame 0, so it's independent of q1, as well as independent from the fact that you're rotating the last joint q6. So it's a handy way for generating one single equation where you have already removed 2 out of the 6 variable. Okay, and there are other ways for generating this. Okay, now the 4 equations in the 4 unknown that Mansur and Doty generate may be solvable in closed form, or you should use a numerical method for solving them. Once you have a solution for Q2 to Q5, sorry, you go back to the original one, you fix those numbers, and what is left, it's clearly you have simple equation in Q1 and simple equation in Q6, and you complete the solution. Okay, of course, I cannot do an example which would take 2 hours, okay, but it's important that you get the point. So this is the last dot there, the last bullet, systematic way for generating reduced set of equations. This is what I meant. Now, let's say some word about if it can be found. So there was a PhD thesis by a PhD student, Pieper, at Stanford in '68. He was a well, okay, it's not important. He was a student of a famous professor. And he proved in his thesis that there could be some sufficient condition, and what was important was handling the most difficult case where it makes sense to look for closed form solutions. So the 6 degrees of freedom case, in particular 6 revolute joints, as we mentioned already. And he found these 2 sufficient conditions. The first one says that if you have rotational joint axis, 3 consecutive in the chain that are incident, for instance, if you have a spherical wrist, or if you have a spherical shoulder, or if you have both, of course, then this is sufficient for saying that you have a closed form solution to your inverse kinematic. That's a powerful result. How was it obtained? Well, using algebraic method. Essentially, he was able to convert the problem into a factorized product of 2 polynomials of degree up to 3. And you know that you have a closed form solution for polynomial equation of degree up to 3, actually up to 4 also. Okay, from 5 on, you don't have a closed form solution in general. Okay, you may have some specific equation that can be solvable in closed form, but not in general. Okay, so this was the idea. In our case, this will be very important, for instance, for robots with spherical wrist. Many robots, not all, but many robots have a spherical wrist. So this sufficient condition is very important. Or if you have 3 consecutive rotational joint axes that are parallel, this is also okay. Is this one of the cases that we encountered already? Scara type. It's correct or not? Scara type, we have revolute, revolute, prismatic, revolute, all parallel. So it's not 3 consecutive, but it's still okay, because the prismatic and revolute, this is the physical order, but if we interchange it into the change, nothing happens because it's a rototranslation around the same axis. So it can be represented as revolute, 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 prismatic as well It makes no change in the direct kinematics. So this is one of the cases. So you were right, although some extra reasoning was needed. Okay? Now, if those fails, we cannot say anything. They are sufficient conditions. So if they are not satisfied, we may find, or we're not able to find a solution. We don't know if we are not smart enough or if a solution in closed form does not exist, in fact. I'm not aware of necessary condition. If you had also necessary condition, you may say, okay, I'm checking those conditions. If they are violated, I'm sure that I don't have to spend time for looking for a closed form solution. Okay, so what is the alternative? Numerical method. Numerical method means an iterative algorithm that you start in some initial guess and you update your guess until you find a solution. Okay? And there could be many iterative methods. So when do you use them? Well, certainly if you are in the redundant case, or more in general, if the number of task variables that you have to, as data, and that you have to invert in order to find a solution in terms of the n joins with n larger than m, then you may have typically, in the generic case, you have infinite solution. We have seen that last time, okay? So if you have an infinite number of solutions, how could you generate this with an analytic expression? It's impossible, okay? You should have an infinite bunch of equations giving you those numbers. So it's so this is the case where it's certainly needed. But of course, if somebody gives you a robot and you don't want to spend time or break your head looking for a closed form solution, even if those conditions are satisfied, you may still need to solve them, then you can set up a numerical method. Okay? It's easy. All that you need is to build up this famous matrix that we will encounter later on again and again, which is the Jacobian, and I would say the analytical Jacobian, of the direct kinematic maps. You see that in this case, it's very convenient to write the direct task kinematic, we called it, as a function r equal a function f of q, because this is a vector function and we carry the subscript r to remember that we are thinking about the kinematic of a specific task described by the variable r. So we take this vector function of a vector variable and we take the gradient. And this is the Jacobian matrix. Remember that the way in which we do derivative, I would like to be very, very clear at this stage. Suppose that you have h, a function that goes from R1 into R1. So h of x, a scalar function of a scalar variable. Then you define, well, dh over dx or dh over dx, because there are no other choices. And this is a scalar. It's very important. Now, suppose that h is a scalar function of a vector argument. Okay, so you have h of x, and x is a function of Rn. Then, if you do dh over dx, this is dh over dx1, dh over dx2, up to, it's a row, not a column. Pay attention, okay? In order to make a column, you use this notation with the nabla h with respect to x, which is nothing else than dh over the x transpose. So I know that this is not always the convention that is used. You'll find books where you find this as being defined as a column. But I think that this notation is better, because if you have now a function, a vector function of a vector argument. So when you have x in Rn, and you have h of x in Rm. Now, what is the h of the x in general? Well, you repeat this for every component of h. So h will be h1 of x, h2 of x, up to hm of x. If you use this convention for writing gradient or partial derivative, then you repeat this for every element of h. So you will have dh1 over dx1 up to dh1 dxn, and this is the first row, as if we had m equal 1, only one scalar function of a vector argument. Okay, and then you border things. So the second row will be dh2 dx1 up to dh2 dxn, and the last column, the last row, sorry, dhm over dx1 up to dhm over dxn. So this will be a m by n matrix. Okay, and this will be our Jacobian, that one. In our case, f is a vector function with m component of the joint variable, which are n in general. So this is a m by n matrix, and we call this matrix the Jacobian of the task kinematics at hand. Okay? Question on this? Good. Now, based on this Jacobian, we can set up numerical methods. And these methods, they will be slower than that. Why? Because we have to make iteration. With an analytic solution, we have just to evaluate this inverse function, and we're done. Okay? However, they are very convenient, and there are many methods. We will recall in this presentation only two: the Newton method and the gradient method. Have you ever heard about this method, numerical method? The Newton method for solving set of nonlinear equations. Did you encounter this in some basic course on calculus or numerical methods? I see one says yes, all the rest yes. Who has never heard about the Newton method? Ah, very good, very bad. Actually, this is something that should be in the suitcase of every engineer, just to make sure. So you will hear from me now, but remember that this is used everywhere in engineering. And the gradient method is another method for solving a set of nonlinear equation, like our case. But in fact, it solves this by solving an optimization problem where we minimize some function. Did you ever encounter the gradient method for minimizing a function? No? Less than before, more than the Newton methods? Okay, well, we'll hear about that. Okay, so these are general methods, but we will apply it to the problem of finding numerically a solution to the inverse kinematic problem of manipulators. And our main core will be this matrix. You will see it right later on. Okay, so let's start with some example. Now, first, closed form method. I will give you 2 or 3 examples of inverse kinematic, which are significant. Let's start with our old friend, the planar to R manipulator. The first thing to do is to write the direct kinematics. You don't go around without this if you want to solve it analytically. Okay, so in our case, Px and Py are the data. So I give you two numbers here. And I want to find the Q1 and Q2, which are buried inside those compact notations. So remember, S12 means sine of Q1 plus Q2, and so on. So the Q1 and Q2 are the unknowns. Okay? So how would you solve this equation? Now you need some intuition, geometric intuition. For instance, I've canceled that. For instance, you can think about this distance. Remember, if I'm giving you a position, Px, Py, in the plane, suppose here, now this distance from the base to here may not depend on Q1. Think about it, just the distance. Of course, you have to look at this point, and this is a function of Q1. But just the distance, it may be the same if you're here, if you're there, and this depends only on the internal variable, on Q2. Okay? So let's build this function. How do? We just square and sum these two equations. Smart enough? So look at this. On the left-hand side, we have Px squared plus Py squared. On the right-hand side, we have to make squares. So we will have L1 C1 squared, but then from the second equation, L1 S1 squared. If we add up, this will be L1 squared, because sine of square of Q1 plus cosine square of Q1 is 1. Okay? Then we will have the same square of the second term, L2 squared C12 squared. Then when we sum the second equation, L2 squared sine of the same angle square. So again, L2 square. So we have L1 square and L2 square, which are data, because we know the length. We carry to the other side, and we have this. What is left? The double products. So we will have 2L1, L2 cosine, cosine, plus 2L1, L2 sine, sine. So cosine of an angle, cosine of the other angle, plus sine, sine of the two angles. And this is a basic trigonometry identity, which gives the cosine of the difference of the two angles. And since the cosine is an even function, it doesn't matter in which order you take this. So you have Q1 and Q1 plus Q2. If you take the difference, you remain with Q2. And this is what you have here. So as expected, I've built one equation in only one unknown. Okay? Now, how do I solve for Q2? I should resist, again, to the temptation of making an arc cosine. I could divide by 2L1, L2 here, so I have a number, which is equal to cosine of Q2. Then I make the arc cosine of this number, and I get a solution. Don't do this, but do the usual trick. You isolate cosine of Q2 as before, so you divide it by 2L1, L2, and this is a number which represents cosine of the unknown. And the sine of the same angle is just this other number, which is 1 minus cosine square. This is a number, it's this number square. Then you extract the square root, and you have to carry 2 sine with this. Okay? So now you have two numbers which represent the sine and the cosine of the same angle, and you solve with the arctangent function with 4 quadrants, or atan2 function, because it has 2 arguments. Okay? We have encountered this already, and now we are using it again. Okay? And this is Q2. That's it. We have a closed form expression. This is analytical form, although it doesn't seem so, but in fact it's a function of 2 arguments, and these 2 arguments are numbers, are this number and this numbers, which carries 2 signs. So in fact, there are two solutions, depending on the fact that you're putting here the plus or minus in the first argument. Okay? The other thing which is very nice is that we have a check that the data are within the primary workspace. Why? Because this is a cosine of an angle. So it should be between -1 and +1. Now if you look at this, now we do another computation on the blackboard, very simple. Which is, I'm rewriting there, px squared plus py squared, then minus L1 squared minus L2 squared, divided to L1, L2. This should be less or equal than 1 and greater or equal than -1. Okay, now analyze this first. This is a positive number, so we can multiply by it and don't change the order of the inequality, and then bring these two on the other side, and we have from here px squared plus py squared less or equal than L1 squared plus L2 squared plus 2L1 L2, which is equal to L1 plus L2 squared. So in order to be solvable, the distance of this point from the origin squared should be less or equal than L1 plus L2, which is the outer boundary of the workspace. If your data, px and py, are too large, you will be out of the workspace. And so this check will automatically tell you that you cannot solve the problem. What about the the left-hand side? Well, similarly, px squared plus py squared. Oh, sorry, I will write it the other way. So multiply by this, bring this to the other side. There's a minus here. So you will have here L1 squared plus L2 squared minus 2L1 L2 less or equal than px squared plus py squared. But this is, pay attention, just the square of the difference, and you don't care about the order. Okay, so if L1 is equal to L2, this is trivially satisfied. So this is 0, and you're saying just that the distance of the point is greater or equal than 0, which is always the case. If L1 and L2 are different, then there's a hole inside the workspace of radius modulus L1 minus L2, and this tells you exactly this. You should not be inside those inner circle of radius L1 minus L2 in modulus, no matter if L1 is larger or smaller than L2. Okay? So you see that from the formula you have a check of the data belonging or not to the primary workspace, so that you can proceed and solve something. If you don't do this, you still can call this, but you don't realize what's going on. So this is a check that you should do before applying this blindly. Okay? So what about Q1? Now I'll show you two ways for solving for Q1, which mimics the idea of having geometric introspection or applying an algebraic method. This is another very nice example of applying a geometric method. First, the algebraic method. First, the geometric approach, which looks at the robot. Now we have found Q2. Okay. We need Q1, but we realize that Q1 is the difference of two angles. One is the angle alpha pointing from the base to the desired point position of the end effector, and beta is that angle there. Okay? So, with the sign that depend on the drawing, but they are always alpha minus beta, then alpha and beta may be positive or negative, remember? So these are expressions that are always valid. If you take the idea how you find alpha and beta and when they are positive and when they are negative. We commented already on that. So you can write alpha and beta in the following easy way. If you look at alpha, so it's a point, it's an angle pointing to P, and so you have that Px is the the cosine of this angle, and Py is the sine of this angle. So you do sine, cosine, arctangent, and this is the alpha angle. And then the beta. Beta is slightly more tricky, but if you look at how beta is made, again, you can recognize sine and cosine of two angles. One is the cosine is the first link plus the red dashed segment, so it's L1 plus L2 cosine of Q2. And this is the cosine of beta, and you place it there, while the sine of beta is just the second link, L2 sine of Q2, and you place it here. Remember that you have already S2 and C2 from the previous, the numbers. C2 is one number. S2 is a number with a plus or minus. So you have the two options that should be carry over and provides you two associated solutions for Q1 as well. From this element. This is data, and these are derived from data. So at the end you have two solutions. And here are their representation. You see that Q2 was found with the previous slide, and since the only difference is this positive or negative sign of the first argument of the arctangent, this changes only the sign of the resulting angle. So Q2 and prime and Q2 prime, the two solutions of the previous slide, they are specular with respect to this axis. You see, they are closing in the same way. So if you find Q2 prime, let's say 35 degrees, you're sure that Q2 double prime will be minus 35 degrees. Okay? While Q1 prime and Q2 prime, the two solutions that you get from this formula, they are no relation. This depends on where is P and so on and so on. Okay? These are opposite, but these two are in no special relation one with the other. Okay? And you can call the red solution, let's say, elbow down, and the green solution elbow up. Or if you flip this on the plane, on the horizontal plane, this may be the right arm solution or the left arm solution. It's just a matter of how you want to call. Important is that it's clear what you're doing. Okay? Question on this? Now pay attention. Pay attention. You remember what I said about the output values of atom 2? So the codomain of this function is between minus pi and plus pi. Now if you make the difference of 2 of this function, what is the codomain? You have a problem here. Because if by doing this computation I get some angles which is, let's talk in degrees, instead of being between minus 180 and plus 180 degrees, is 270 degrees. You should bring it back to minus 90 degrees. Why? Because if you have a joint range limit now, which says that you have to be with angle Q2 within plus or minus 120 degrees, and your result is 270, you would say, I'm out. In fact, you're not, because you are minus 90. Okay? So pay attention. All the limits of the joint range are removed from this analysis. First, you compute a solution without limits, and then you check if you're inside the limits. You may also discard one of the two solutions just because one is out of the limits. For instance, for my right arm, if I'm finding angle Q1 and angle Q2, then if I keep my right arm, I cannot implement the other solution because I'm out of range with my Q2. I cannot flip to the negative value. So I can compute both, but then I keep only those solutions, in this case 1, which are satisfying the joint limits. Okay? Which is a very convenient approach. You can bear with me. Okay, so this is good, but then you have to do some post-processing before outputting your solution. Huh? Well, there's another way of doing things which uses only one arctangent function and so automatically avoids this problem of mapping back the solution. And this is an algebraic approach. I think that this slide is very pretty. Maybe you don't agree with me, but so it says, okay, I have found Q2. Now I have to find Q1. I look back at the algebraic expression, so no geometry here. And I see that these were the two nonlinear equations. Now I expand the sum of the cosine and sine of a sum of angles, and I obtain this expression in parentheses. Now I make the following trick. I don't want to solve for Q1, but I have two equations in two unknown, which are sine of Q1 and cosine of Q1. In terms of these two unknowns, which are clearly related, these equations are fully linear. Okay? So, in fact, I can reorganize them in matrix format, just bringing things in the proper side. So these are the two unknowns, and this is a matrix of numbers, y, because L1 and L2 are data, and now as sine of Q2 and cosine of Q2 have been computed already as function of the data. Again, sine of Q2 carries a sign, so this computation is done twice, one for the plus, one for the minus sign, so to generate the two solutions. And then I solve this linear system of equations, 2 by 2, very simple. Can I always solve this or not? And this gives another clue that this method is superior. When I cannot solve this equation? Or can I solve it all the time? How do I solve this equation? This system of equation, I would say. This is of the form A matrix X equal B. So X is A to the minus 1 times B. So I have to invert that matrix. Can I invert that matrix? I should check if its determinant is different from 0. And if you look at the determinant is this expression. Okay? Pay attention, there's a cosine here. If it was like this, then it's clear, different from 0. It doesn't mean to be positive or negative. It should be different from 0. Now, this is always positive, except in one case, when L1 is equal to L2, and the cosine of Q2 that you have computed in the previous step is equal to minus 1, which means that you're folded. Now, if you're folded and you have equal link length, means that your data were be in the origin. And of course, I cannot solve for Q1 because I have infinite solution. And so I cannot invert this system. As neat as that. So just checking this tells you if you have infinite solution or not. If you have a robot with different link length, you don't even care. Then this will be certainly different from 0. Why? Because you're solving like this. This would mean if cosine of Q2 is minus 1, you would be in a situation like this. So you have found that Q2 was equal to pi, and now you will find that depending on the desired P, you will find also a unique value for Q1. When the two link lengths are equal and you are in this situation, to be minus 1 means that you are in that case in the origin, and then Q1 cannot be defined uniquely. So you skip this case. Otherwise, you solve for C1 and S2, and then you do the ATAN 2, which in terms of the data, I've written it like here, with a division by the determinant. Okay? Again, you have to check first the determinant, and then you apply this formula. So in your code, this should be clearly organized. So this is the second solution, and in fact, these are the good notes. This method provides directly the results in minus pi plus pi, because it's just an arctangent, just one. Okay? And moreover, since when this is different from 0, so you use this formula, otherwise you don't use it, then it is positive. And since this happens to be at the denominator of both arguments, if you remove a positive factor from both arguments, you obtain the same result. So you can avoid to compute this and just have the arctangent 2 of this without the determinant at the denominator. Okay? That's it. So we have seen that in the first part, we have checked if we are inside or outside the workspace, and if we are inside the workspace, we compute the Q2. In the second part, we compute the Q1, checking the only case where Q1 is not defined, so when L1 equal L2 and cosine of Q2 is minus 1. Okay, and that's it. So in any event, we may find two solutions, the generic case, or a solution for Q2 but infinite solution for Q1, a singular case, or even that the two solutions collapse into one, and this happens when we are straight on the outside boundary. Then the right arm solution and left arm solution collapse into the same solution. So this plus or minus doesn't generate two different solutions. Okay, so we have all cases. And we are satisfied because we have found all these cases in closed analytic form. It's a very simple case, I must admit. So let's consider one which is three-dimensional, just for three-dimensional in space. And our task now is just positioning the end effector of this polar or RRP arm. You remember that we consider this. So first we have to derive the direct kinematics. Pay attention. Here I'm using data or definition of variable which are not fully Denavit-Artenberg coordinate. Okay? I'm just defining angles in a very direct way. I'm not using homogeneous transformation matrix, even if I'm working in the three-dimensional space, just because it's easy to derive the position of the end effector for this polar robot in terms of the three angles that I'm introducing here. As an exercise, find if you're using the correct Denavit-Artenberg notation, you will see that the angle Q2 is defined in a different way, not the angle from the horizontal plane up to link 2, okay, like I wrote here. Now, do you agree that these are the correct direct kinematic expression? For instance, PZ is this distance from the origin to the elbow plus this height, which is just the distance Q3 times sine of this Q2 angle, just the elevation, okay? While if you look at this, which is then divided into Px, Py by sine and cosine of this Q angle, this is just the projection of, it's this one, which is Q2 cosine, which is Q3 cosine of Q2, and then you divide by sine and cosine, and you have Px and Py. You distribute by sine and cosine. Okay? So it's very simple to derive direct kinematic equation. Now again, suppose that these are the data, and we have to solve for Q1, Q2, and Q3. How do we do? Again, maybe this idea of finding distance is okay. Huh? So, what if we square and sum the three equations? Does it make sense? Well, not completely. Why? If you square the third equation, you have pz squared on one side, and on the right-hand side you have d1 squared, which is a constant. Then you have q3 squared sine of 2 squared, but then you have also 2 times q3 sine of 2 squared d1. So again, a function which is of q2 and q3 together. Okay? So this does not work, but a slight modification makes more sense. Namely, before doing squaring, you bring this d1 to the other side. Okay? If you bring d1 to the other side, it's a constant. Huh? d1 is some Denavit-Artenberg parameter or some geometric quantity that it's given, and pz is given, is the data that you have to solve for. So pz minus d1, and then you square. Then you generate here a square of something that will simplify with the squares of something in the first and second equation. It's a simple trick. In fact, what you're doing, you're computing the distance not from the origin to the end effector, when the end effector is in px, py, pz, but from this point. So you're removing from pz this distance. So you're computing the distance from the shoulder to the tip. And this is only a function of q3, I would say. Okay? In fact, performing computation, doing the following, you see that you have q3 squared in all right-hand side once you have brought d1 to the other side. And then on top you have cosine 1 squared, cosine 2 squared, then sine 1 squared, cosine 2 squared. So you eliminate sine and cosine of q1, and you have only cosine square of 2. And then here you have sine square of 2. When adding, this becomes 1, and so you're left with q3 squared. Magic. But the idea is always the same. Find some expression which should be independent from as many variables as possible. In this case, it's just q3, which is just the distance of that point from the shoulder. It's the definition of q3, only squared. Okay, now you have to take the square root of this, and now you have to decide if you want to carry over the plus and minus sign or just keep the plus sign. And here, just for the specific choice, we just take the positive value. In general, you have also the minus, which means if you're in this configuration and at the desired point, certainly there will be another solution with q3 negative, which means rotate and then retract this arm. I cannot do it, and extend it negatively to that direction, to that position. Okay? So typically this is not possible in prismatic joints because you have limits. And so I decided just to take one sign here, just positive q3. But in general, in principle, you should take also the minus sign. So you're taking half the number of possible solutions by just taking one sign here. Okay? So, and now pay attention. Here we have a lot of strange cases that may happen. And in fact, we will see that this corresponds to the singularity of the Jacobian of this robot. Okay? Now, you have solved for q3, and it may happen that q3 is equal to 0. For instance, if you're wishing to be in that point, so at the center of the shoulder, although physically it's not possible, but if you take just the skeleton of the robot, this still makes sense. So px is 0, py is 0, and pz is equal to d1, then q3 is 0. Now, if q3 is 0, everything disappears, and so you don't have equation available for solving for Q1 and Q2. And in fact, these remain both undefined, and you have to stop with your solution. So when I'm retracting and I should be here, then it's not important if I elevate the link, because now it's retracted and this elevation doesn't change the position of the end effector, nor the rotation of the base will change the position of the end effector. So Q1 and Q2 are arbitrary. You have infinite to the 2 possible solution. Okay? If instead this is different from 0, well, Q2, for instance, is obtained from, let's say, the second and third equation. So you take this Pz minus d1, you divide by Q3, which is positive, and you have sine of Q2, and then you square and sum the first two, sorry. So you eliminate Q1, but then you have the square of C2, and here it is, and then you extract the square root and you carry 2 sines. Okay? So in general, even if you have only one Q3, so the positive one, you will get 2 solutions for Q2. Okay? What about Q1? Well, Q1 it happens to be only in the first 2 equations. Now, in the first 2 equations, we have Q3, and we have sine and we have cosine of Q2. Now we have already eliminated the case where Q3 is equal to 0. Now we should also eliminate the case where C2 is equal to 0. Because if C2 is equal to 0, then those vanish, and there are no equation for solving for Q1. So when do they vanish? When the data are such that px squared and py squared is equal to 0, which means, pay attention, not that we are retracting here, but we desire to put the end effector on the vertical line going through the first joint. And of course, if we are here, no matter which height, and this is regulated by Q3, and Q2 is also defined as 90 degrees, or minus 90 degrees if you want to, and then no matter which value I give to Q1, I will solve. So I have an infinity of solution for Q1. And again, I should stop. Okay? So if I'm not in this case and not in this case, I end up also with a solution Q1, and because of this plus or minus sign, I have 2 regular solutions, Q1, Q2, Q3. If I was carrying the minus sign here, in that case, I would have double the number of inverse kinematic solutions to 4. Okay? And you see, less than 8, just because there's one prismatic joint here. In a 3R articulated arm, we have seen that we have 8 solutions, typically. Okay? Now, pay attention, because we will come back. There are 2 remarks. First of all, in this part, I have eliminated Q3, because Q3 in this case has been chosen as positive, so it's a common factor at the denominator which can be eliminated, and the result is still okay. So it doesn't change quadrant. And wherever the algorithm stops, then you are in a singular case, and you may have infinite to the 2 in this case, or if you don't stop here, you stop here, then infinite to the 1 possible solution, because here Q1 and Q2 are undefined, and below Q1 only is undefined, while Q2 has been defined by this expression. Okay? I hope you're still with me, and this is the last case we will see for the analytic solution. And it's a general case. This covers many other cases. It's very important, and it's the case where we have, let's say, a 6 degree of freedom robot with a spherical wrist. Then peepers sufficient condition tells us that there is a closed form solution for this case. Okay? How do we find it? We found it by a method of divide and conquer, I would say. So here is the situation. You have your robot with 6 degrees of freedom. The first 3 are any type. Revolute, RRP, PPP, whatever. Okay? The first joint is somewhere here, and this is zeta 0 axis. And then when you get to the last 3 joints, joint 4, joint 5, and joint 6, because this has a spherical wrist, they always intersect in a common point. Okay? So we call this point W, center of the spherical wrist. And for sure, we have that Z3 is along J4 and Z4 is along J5, and this will intersect in this W. Okay? And then we have also Z5 that is on J6, and then we may have the last frame, frame 6, which is placed somewhere, but according to the Dynavit-Artenberg convention. There is some degree of freedom for doing this, but what is certainly true is that we will have the X6 axis orthogonal and incident to the last joint axis defined, so to the joint axis 6, so orthogonal and incident to Z5. And then Z6 is along the approach direction. Okay, this is our choice. We can always choose things like this. Okay? So this is the picture. Now, what is the inverse kinematic problem in the classical sense? So let's give a value P for the origins of O6. So for this point there. It should be somewhere. And then give an orientation to frame 6. So a rotation matrix of numbers. And in particular, the last column is, again, numbers, characterize the direction of Z6 in the absolute space, so in terms of frame 0. Okay? So these are the data. Now, from this data, we can elaborate on these numbers so to extract one basic information, namely, where should the center of the wrist be in this situation? And there's a unique solution for that. So, if you take the number, the vector P, which means where should the origins of 6 be, and you subtract a unit vector A, which is the last column of the data. So, in this direction, you're subtracting the scalar D6. So, you're moving the data from the origins of O6 to where the center of the wrist should be. So you have 3 numbers that tells you where the center of the wrist should be. Now, this positioning of the center of the wrist depends only on the first 3 variables, Q1, Q3, and Q3. Why? Because if you rotate around joint 4 by the angle theta 4, well, this does not change the position of W. Same if you rotate around J5, same if you rotate around J6. So theta 4, theta 5, and theta 6, which are the coordinate Q4, Q5, and Q6 in this case, because these are revolute joints, they do not affect the position of W. So I'm sure that if I compute just the position of W, so some origin, intermediate origin in the change of homogeneous transformation, I will have a function only of Q1, Q2, and Q3. So I have decomposed the problem. I don't know yet what are the value of Q4, Q5, Q6, but depending on what are the joints of the first 3, what are the nature of the first 3 joints, I will solve for this problem, for instance, using the previous equation. If the robot is a polar robot, the first 3 joints are of the type RRP, and if you give me a desired position for W, we have just find a solution for Q1, Q2, and Q3. Okay? So the solution for the main joints, how they are called.
What if the joints number 5 or 6 is prismatic, which is not super?
Then it's not a spherical wrist. Okay, spherical wrist means the last 3 are revolute and with, okay, good point. So only for that case. But this is a very relevant case, you can see. Okay, so now how many solutions you find for Q1, Q2, Q3? Well, this depends on what are the main axes. You may find, like in the previous case, 2 for a polar robot where you just eliminate Q3 negative, or you may find 8 solutions. It's not important. You find those solutions in closed form, for sure, because the problem is reduced. Only 3 unknown, and the analysis of Pieper, which is very general, tells you that you will find a solution for that. Okay? Now, what else? Now a bit of magic. Now you know that this rotation matrix in the, let's write it again here. Your data T06 are written as RP 0 transpose 1. So these are data. And you know that these are obtained by the product of homogeneous transformation matrices, but in particular, that this part is just the product of the rotation matrix inside the homogeneous transformation matrix. Up to 5, 6, Q6. Okay? We have shown this. No? The rotation is just the product of rotation. This position is a combination of things, but this is always true. So we have assigned a desired value to this rotation matrix, and we know that this is the product of this 6 rotation matrix, which I organized in 2 blocks. One is from 0 to frame 3, which is a function of Q1, Q2, and Q3. And there I put these numbers. If I put these numbers here inside, this becomes a known matrix of number. And then R36, which is a function of Q4, Q5, and Q6, which is the rotation matrix due to the rotation of the last 3 joints, Q4, Q5, and Q6, around the sequence of axes, of joint axes. Okay? So this is given. This is known once we plug in one of the solution of the first subproblem. And of course, we have to repeat this for any solution that we find for the main 3 axes. So for each, I repeat this problem. While this, if I look at carefully, I will recognize that this is a rotation matrix of the form of a Euler, so moving axis, either ZYZ or ZXZ sequence. Okay? Very simple. So I pre-multiply by the inverse of this matrix, which is known, and the inverse is just the transpose. So the given data orientation that I need to reach, pre-multiply by R03 transpose, becomes a rotation matrix, and I should solve this inverse problem of representing orientation by a minimal sequence of angles, Q4, Q5, Q6, like we did in general for the Euler case. Now this Q4, Q5, Q6 are in fact the joint angle of the spherical wrist. Okay? You see that everything comes together now. Now, why did we analyze this? Because here is one nice application. How many solutions will you find here to this problem in general, out of singularities? How many triples Q4, Q5, Q6? You remember? In general, 2. 2 sequence of angles generate the same orientation matrix. So you will find 2 solutions there. You will find 2 solutions for Q4, Q5, Q6 for any solution here. For instance, for a unimation puma, you will find 4 solutions here, and then for each 2 solutions for the spherical wrist angle, so a total of 8 inverse kinematic solutions. Okay, so summarizing, this is the inverse position kinematic for the mind axis, and this is the inverse orientation problem for the spherical wrist. Pay attention, this product, how do we interpret this product? It's mathematics, but we can give a clear view. So we're trying, with the first 3 angles, once we choose any 3 angles, the frame there will have some orientation. Now, the last 3 angles are those needed to add some additional rotation so that the final orientation of the frame 6 will be the one desired. So we are just multiplying rotation matrix and isolating what is missing. Okay? So this transpose should not be some strange things. It's just that you reverse things. Okay. So, this is the Unimation Puma 600, or there are several similar Puma arm. 560 is the same. Here there is some assignment of frames, and this is the direct kinematics. Looks horrible. Inside here you have, let's say, sine of Q1, sine of Q4, sine of Q6, cosine of Q6, cosine of 5, sine of Q2 plus Q3. You have all the 6 variables there. In fact, these are the unit axis corresponding to x6 as a function of the q variable, the unit axis corresponding to y6, and the unit axis corresponding to z6. Okay? So these are numbers. It's changing the notation, but these are numbers. Here I'm using the notation that we have used in other slides. And given these numbers, so NSA means this rotation matrix of data is given, and we have to solve for all these variables. Okay? And the last one is the position of the origins of the 6th frame. However, look at this table of Denavit-Artenberg parameter. Here you see also the ranges, but this is not important. Here you see the theta's, and these are the variables. Here you see the D's, and you see the A's, and you see the twist angles. And look at D6. D6 is 0. So in this case, the authors have already chosen the origins of frame 6 in the wrist center, because this robot has a spherical wrist. So instead of using some points outside, he just removed this. As a consequence, if you look carefully to the expression of the position of the origins of 6, which is automatically the position of the center of the wrist. So in this case, we should not manage to remove this. In fact, this expression, although complex, is just a function of Q1, Q2, and Q3, as expected. Okay? So although you have to solve this tremendous set of equations, the theory says that you can find this solution in closed form, and there will be 8 different inverse solutions for this arm, and you can find all the procedure in this paper by Richard Paul and Shimano and Meyer, which you find in your material. So even this way of generating independent equation by pre-multiplying or post-multiplying by homogeneous transformation is in the same paper. Okay? So if you're interested in the details on how you generate equation and solve this, you have it there. Okay, I think that we could stop here. We could stop here and leave the numerical approach to Friday. Okay? Bye-bye.